So I'm going to be talking about cosmic dawn with two of my favorite telescopes. Some of my favorite telescopes. I must say I like the far side and far view too. That's just a plug for Jack, but no, that's true. But we will talk about edges and OVRO-LWA today. And the work with edges, like Sebastian mentioned, I started at ASU, so I've left my SU position in, and at Caltech I work with OVRO-LWA. Right. So whenever I talk about cosmic dawn, I like to put things in perspective, and I like to do that with this timeline of our universe, having Big Bang to the present day, after about 13.8 billion years. Now, if you look back from the present day till about 12.8 billion years, we have a lot of different telescopes probing different aspects of the universe. I'm sorry if I missed out your favorite telescope. I should also probably include JWST probing a little further, but these are some of the telescopes that look at as far back as 1.8 billion years. And if you come forward from Big Bang around the CMB, we've studied it extensively with Kobe also, but Planck and WM. Now, in between, this period of when the exciting phase of the universe, if I may, started from dark ages to cosmic dawn, and the very first structures of the very first sources turned on, we have some telescopes like EDGES and OVRO-LWA, but among many others that we touch upon, that actually probe the cosmic dawn in total. So maybe JWST will look at few bright sources turning on, but these, with 21 centimeter cosmology, with radio telescopes like this, you're actually going to study the complete thermal history of the IGM at that period, the actual evolution from dark ages to cosmic dawn to ER, the whole picture. You need 21 centimeter cosmology. And how do we do that? Simply because we use the most ubiquitous matter present then, neutral hydrogen. That's it. Right? So we use that, and we use one particular signature with it, which is the spin flip transition, which radiates at 1.4 gigahertz or 21 centimeter, hence the 21 centimeter cosmology. To just give you an overview, this is a little cartoon of the hydrogen atom. The spin flip occurs when your spin axis of your nucleus and electron are aligned to anti-aligned. It goes from aligned to anti-aligned, it emits 1.4 gigahertz. But let's remind ourselves, this radiation that we're looking for is way back in time, so it's redshifted to frequencies below 100 megahertz. Hence, I use EDGES and OVRO-LWA, which operate below 100 megahertz. Also, it's nice to remind ourselves that this signal that we're looking for is really faint, about tens to maybe hundreds of millikelvin, but still very faint compared to our foregrounds. At these frequencies, the foregrounds are about 10 power 4 to 10 power 5 Kelvin. So, yeah. Now, wait, I should probably move that. That's annoying. One second. Yeah. Okay. So there are two approaches to go towards 21 centimeter cosmology. One is you can measure the globally average signal. So you use just one antenna. You're looking at the globally average signal on the sky. And you're actually measuring the differential brightness temperature. So you're measuring the contrast between the temperature of the neutral hydrogen gas against CMB or anything in the background. That's what we're measuring. And this is one such model where I'm showing the brightness temperature of the spin flip transition versus frequency, which maps onto time or redshift. And you can see if you can detect all these phases, you're actually looking at the different cosmic epochs. Now, some examples of instruments that are actively working on this. One is, of course, the EDGES instrument in Western Australia, which we'll talk about in detail. Other instruments are SARIS in India, REACH in South Africa, but led by the Cambridge group. And MIST is a telescope placed in McGill Arctic Center. It's a portable telescope. Right now, it's in McGill. They took some observations, but they are very portable, so they go different paths to take observations. So these are a few of those. The second approach to go for 21 centimeter cosmology is actually measuring the power spectrum, or like actually measuring how your or when that has the sources turn on, how they create ionizing bubbles around it as they ionize the hydrogen. So they actually measure the variation of neutral hydrogen, not just along line of sight with the global measurement, but also along the plane of the sky. So I like this little simulation by Metwin. So on the left, you're seeing an image, cosmological image cube being simulated. The dark patches are neutral hydrogen, and the light fluorescent green is when the stars turn on and ionize hydrogen around it. Correspondingly, what we measure when this happens is this power spectrum. On the x-axis are K modes, which is nothing but maps onto baselines. So lower K modes, you're looking at larger structures on the space, and higher K modes, you're resolving smaller structures in space. So this is what we go for the interferometric approach. And few telescopes that do that, OVRO-LWA in Southern California and Bishop, Hera in South Africa, and the LOFAR in the There we go. So for both approaches, there are common challenges. One of the first things that you can guess, like I said, the signal we're looking for is really weak. The first challenge we are dealing with is foregrounds. But if it was just the foregrounds, that we could have captivated the difference in the spectral properties of the foregrounds and the signal. The signal is expected to vary quite fast with frequency, whereas the foregrounds have a smooth spectral structure with the frequency. But we have a lot of things in the way. We have hydrosphere, which adds more spectral structure. We have our own instrument beams, which I have worked on extensively, and I will show you some plots that make the foreground coupling to the signal even more complicated because the beam has chromaticity. And then, of course, there's the receiver gain that varies with frequency. And the last, not so obvious observational challenge is the analysis, which I will touch upon. And with this ionosphere, here's my plugin for lunar radio observation. So with the ionosphere thing, I think I'm not going to touch upon Farsight, but that's another telescope or concept that I worked with extensively. I think the next frontier for 21 centimeter cosmology, we're going to be talking about cosmic dawn. But if you want to do 21 centimeter cosmology for dark ages, which is the only probe for dark ages, we'll have to go to the pole. But that's probably for a discussion on another day. Anyway, with that introduction, EDGES. EDGES is the telescope in Western Australia. It stands for Experiment to Detect the Global EOR Signature. Now, EDGES is designed to probe not just cosmic dawn, but also EOR, therefore just after cosmic dawn. And overall, the instrument operates between 50 to 200 megahertz. With 50, and we are split into different instruments. So 50 to 100, the low band probes cosmic dawn. 100 to 200, the high band will probe EOR. We also have recently added mid-band, which is between the two, 60 to 120 megahertz, simply because we will talk about it, simply because we wanted to confirm the tentative detection we had in 2018. Now, what does the instrument look like? Very simple. I like to say it's just a simple table. I'm not even kidding. It's about 1 meter by 1.8 meters. It's just a tiny little table, maybe not so tiny, but over a large ground plane. So it's a dipole over a ground plane with the actual receiver below the ground. And two calibration schemes that make EDGES a very powerful instrument are in situ 3-position switch calibration, where every cycle we take 13 seconds of data from noise loads, another 13 seconds of data from another noise load, and then 30 seconds on start. So every cycle we're calibrating, and also another absolute calibration that we do in the lab nominally, but with a new instrument, we're also doing that. We'll talk about it. Okay, this is the entire team with our PIs, engineers, researchers, and one grad student at the moment. Okay, yeah, in 2018, we gave out a paper that was a little surprising. We had a tentative detection of the possible first stars. This was our main detection that we found. So we found the absorption feature of the 21 centimeter signal that could correspond to cosmic dawn. But it was questionable for many reasons. One, they're dead. So it's about 600 millikelvin. Most models predict about at the max 200 to 300 millikelvin. So it's much deeper than we expected. And plus the strange flattened Gaussian shape. So this, if I may very likely say that led to the whole community being a little bit stirred, and we had about 500 papers very quickly coming out. And I like to say there were two categories in the theories. So how do we get such a deep absorption feature, at least mathematically thinking? I showed you this differential brightness you measured against the CMB. So there are two things you can do. Either you increase the temperature of your background. You can't increase the temperature of CMB, but maybe you assume there's another excess radio background. Or you cool the matter faster than adiabatically. That's why there was another category where people thought about baryon dark matter interaction. Then, of course, there's a third category that was like, is this from systematics? I must say, we also fall in the same category. As a team, we have been thinking about what could have caused the signal. Is this our processing? Is this our hardware? Is this our beam? Is this our instrument? So I'm not going to go into the details of this whole matrix, but I want to say we have been active and thinking every possible systematic, additive, multiplicative, non-linear, categorized in 4 different categories, and we've thought of all different tests we can think of to possibly answer the question. Our goal is this summary being green. So basically, we want some tests to answer all the questions we have. And the ones that I have focused on personally are the processor. The way I did that was we developed, after 2018, we developed an independent processing pipeline, completely open source, completely written in Python. And I'm stressing on that simply because in 2018, the pipeline that we used was a legacy C pipeline written by the great Alan Rogers. Like, there is nothing in the pipeline I can ever find is wrong, except that it's a long 10,000 line code with no comments, and I have spent years staring at it, modularizing it into different functions. But there is no mistake. I always thought I'm going to run into something that's wrong here, but nope, that man's a genius. So we did that. So now the pipeline is ready. One main goal was we just wanted something independent. We just wanted to be honest to make sure that every single module was reproducible, every single processing was traceable. And if tomorrow you say, okay, this reflection coefficient of the antenna, why don't you change it? Let's see what happens to the final result. It's possible with the new pipeline now. So with that, and then the new pipeline will accompany Edges 3, which I will talk about. Other important thing that we wanted to do for the community is, now you see, I told you there's Surrey, there's Reach, there's Mist. Everybody, they have different instruments, different receiver, different challenges, but there's some common groundwork. Like, you need to look for this global signal when the galaxy is down. You can use the galaxy up data for calibration. We have a lot of common challenges. So we wanted to make this pipeline interoperable that tomorrow, let's say Mist, as far as it has its antenna properties into our pipeline, they can use our pipeline and process through it. So that would be useful. And this new pipeline, the other additional advantage is the whole thing is in a patient framework now. Okay, so with that, so I spent about 1.5 to 2 years developing, actually just 1 year developing the pipeline. But after that, there was a lot of steps. So these are about 18 steps that went into processing the 2018 data that released. And inside these 18 steps, there are about like 5-6 parameters inside. And you tweak that. I probably chose something different from the 2018. So it took me another year to make sure I was taking the same parameters that legacy pipeline had, just so that we wanted to reproduce what the 2018 results was with a new pipeline so that we can trust it. Once we trust it, we can go off and do our own thing. And we did. So this is a new result from as new as like 4 months ago. I think Josh has seen it, but everybody else, this is new. So what I'm showing you here is the same data that we published in 2018, but processed through the new pipeline. So this is the data, 12-hour average data when the galaxy is down. And the blue curve is the process data with the new pipeline. The dashed black curve for reference is the data from the old pipeline. And you can see they overlap just fine. But what we want is, let's look at the difference. The second plot is showing you the difference between the two curves in the first. So there is about 0.25% difference, but it's smooth. Now, to the top curves, if you just pick a 5-term polynomial, that is the residuals we see in the bottom. So now if you see, overall, we see the same residuals we reported in 2018, but given we are using the same parameters we did in 2018. But this is a nice test that the new pipeline is working. We can produce the 2018 results. Now we are free to do what we want. And that's what we did, and I'll be starting to do. So now in this pipeline step, I will make some changes to see how it affects the final result. Now, I have again a huge Excel sheet with about 30-40 possibilities. I'm just going to show you a few things that we've started off with. Also, I can highlight in this processing pipeline, the green refers to filtering, and the red steps or pink steps are when you make some modification to data. So the first thing I tried was the RFI filtering. I tried to change the algorithm from what was used in 2018 to something else that we thought was more optimal. And you can see it makes some difference, but the difference is still smooth. So when you fit the 5-term polynomial, the residual structures still look the same. And then the other test that I tried was calibration. Receiver calibration is another big step in the processing pipeline. So for an edge style receiver, there are about 7 parameters that go into a receiver calibration. To give you all an idea, the first 2 parameters talks about the scale and the offset of the gain. The next 3 are the noise parameters of the receiver, and the last 2 are the receiver's reflection coefficient. Now, what am I showing you here? The black curves are very close to 0 because I'm showing you that in the black, I used the exact same receiver parameters as used in 2018. And blue is the test I'm trying. I'm using slightly different receiver calibration parameters and seeing what happens to the final result. And you can see that it does make considerable difference to the shapes of the residual. The interesting step would be next thing to fit the flattened Gaussian and see how it affects the parameters, which I haven't done yet. The other thing that I tested was the balun connector loss. I forgot to mention that the signal from the antenna to go into the receiver, it uses a balun, and that has a certain loss associated with it. That loss depends on the actual dimensions of the balun, and in the memos of edges when I scanned, for the same instrument, there were 2 different lengths of the baluns reported. And I was like, okay, I'm going to try the second length and see what happens. So I tried the different length, and you can see it does make some changes to the final residuals, and definitely interesting to look at the actual fitting of the Gaussian as to what it does to parameters. So those are just some of the tests, but like you can see, all of these, at every step, I'm going to make some changes, or switch on, switch off some filters, and see what it does to the final result. So that's one thing about the pipeline. The next thing I'm really interested with the edges data is to test the global signal that we reported. Is it actually global? Like, is it same with time? It should be if it's global, right? So this data that we presented in 2018 was 12-hour average data when the galaxy was down. The test we are going to do next is called what I call the LST bin analysis. You take the 24 hours of data, but break it down in time. So I made 4 chunks of 5 hours each, with 1 hour in between so that there's no beam overlap. And the idea is I'm going to fit different foreground models to each chunk because the sky is changing, but I will fit for one global signal model because that should be constant, and then see what parameters we need. But this is the chunks of data I'm showing you. So this frequency versus residual. So I made the spectra, I fit the 5-term polynomial, and I'm looking at the residuals. It's nice to see that the residuals from both the pipeline match. That was another test. And to this, I thought I'd just show you some inferred parameters. So first check, let's look at each bin. We wanted to make sure that our foreground parameters are physical. Like the T75 looks physical, and the beta is basically less negative when the galaxy is up, and we will find that. So at least physically, that was a nice sanity check. Here, I'm showing you the inferred parameters of the cosmological signal we reported. So there were 4 parameters. The amplitude of the signal, the flatness of the signal, the center frequency, and the width of the signal. So the blue and orange are the LST bin results. And the blue is from the 2018 pipeline. The orange is from the new pipeline. So you can see they overlap quite a bit. They also overlap with the black. Black is the cosmological signal inferred when you average all 12, what we reported. So they are all sort of in agreement, except the sigma parameter, which is noise, and it makes sense, right? So when you average 12 hours of data, your sigma is going to be low, noise is going to be low. So the preliminary results of LST bin analysis looks promising. And where are we going from here? We have a lot of data from edges, actually. Now that the pipeline is set, we have different instruments. Like I said, we have midband, we have edges 3, we have edges 245, where we basically rotated the orientation of the antenna so that it looks at different part of the sky. Now, there's a lot of work to do. The pipeline is tested, verified. We just have to go and crank it up on different data sets. Quickly about edges 3, I kept saying that's the new instrument, and it's really exciting for a couple of reasons. Now, if you see the antenna is no longer a blade, it's a box, simply because we put a receiver inside. So the receiver was under the ground, remember, but now we're putting it inside. The advantage of this is there's no balun. That confusion about the balun connector loss, that's all. And second thing is, in addition to the receiver, all the calibration loads are also inside. So we don't have the hassle of taking out the receiver from the ground, bringing it all the way from Australia to ASU, calibrating the lab, flying it back to Australia. And I must tell you, Alan has seen changes because of that. And that man just like, he knows this thing. He's like, okay, yeah, the SMA connector got loose. I can see that in my results. Like, okay. So now we don't have to worry about that. The other big thing is the ground plane was 30 meters by 30 meters. Now it's 50 meters by 50 meters, which means the chromaticity of the beam has reduced. And what's the status of Edges 3? There have been two things. We have deployed it in, we have a permanent installation in Australia. And since November 2022, we have a lot of data coming in. Yeah, so that's one about Australia. And in Devon Island, we took it in August of 2022. We took it there for about 25 days, but got only 12 usable days. The ground plane was slightly different because we couldn't get the mesh welded, so it was just like a meandering wire ground plane. And the lessons learned from there, since it was August, the sun was always up in the northern hemisphere, and the sun was extremely active, and we saw a lot of RFI because of sporadic eve, and there was also some RFI between 50 to 60 megahertz that we couldn't really explain. So it was just like lessons learned mostly. But this is preliminary results from Redshifted. Very preliminary. This is still the legacy pipeline. It has not gone through the main pipeline. So this is actually Alan Rogers' results. So the green is what we reported in 2018. The blue is Devon Island, even though we just had 12 days. And the red is the Western Australia deployment. We are still seeing this. It's a new antenna, it's a new receiver, it's no balun, it's new ground plane. Whatever it is, we're still seeing it. So that's Edges 3. So that's our overall Edges thing. So we have done a lot of work since the first result, and we're still doing. We have a lot of data. Personally, I worked on the new pipeline. It's ready to go now. The idea is to just process it through more data, test all different processing choices, and then somehow get that LST bin analysis option. And oh yes, I forgot to mention. So the other biggest exciting part is I just got to know about a few weeks ago, I'm going to Western Australia on Monday, which is why my trip is cut short. So for some hardware upgrades. So Edges 3, the ground plane is a little uneven. And when it's uneven, it affects the antenna chromaticity. So I'm going to go out and measure how uneven it is so that we can include it in the modeling. And wherever we can, we're going to clamp it at the soil. That's one thing. And another Edges ground plane is left free. There's no receiver, so we're going to go put a new receiver inside. So these are the two upgrades I'm going to do in Western Australia. It's been 7 years I've worked with the instrument, and this is my first trip. So actually, before I move on to overall, should I like take questions about Edges? Yeah, if anyone has questions about Edges stuff. I've done to overall and then yes.
Are there plans to test different global models?
Yes, there is. Yeah. All those ideas are there. It's just like I think all of it. Like somebody has to work on data, somebody has to work on this. So I think our biggest challenge was first, let's get the pipeline ready. And then I think we'll go out in full force. Yes, we want to try different global signal models. We also want to try and test what Sims et al. And Singh et al. That proposed, where they said if you fit a program model and a sinusoid, that could potentially explain the signal we saw. But I want to test that in LST bin data because preliminary I did it, and that doesn't explain when it's LST bin. When you average it, it could possibly explain, but when you LST bin it, that's not sufficient. Yeah. Yes.
Just the data question. You said that in the pipeline there is several parameters in each step. So are you worried that there might be a degeneracy where like different combinations of parameters get the same?
Oh yes, absolutely. I'm glad you actually asked that question. We are worried and we don't know how to go about it. That's one column in our matrix that doesn't have a yellow or a green. We still don't know what test we need to do. combination of systematics, we still don't know what to do yet.
Right.
We are definitely worried.
Right.
Like an S11 error could look like a gain, or receiver noise error could look similar. An LNA S11 error and an antenna S11 error cannot be separated.
But Alan would know which one is which.
You're right, it is a concern. We don't know what to do about it.
You don't, I'm sorry.
I thought I
Oh, okay. So I don't work on cosmology, but you were saying you can't change the CMB signal, obviously, but there could be some other
Yes. Yeah.
signal.
Yeah.
Why would no other observatories have seen that?
Okay. Correct me if I'm wrong, so I don't know this exactly, but the excess radio background was reported by our cave too, right? That's where the first idea of the excess radio background came up.
Okay.
Has it been confirmed? I'm not sure.
Yeah, I don't think it has, but yeah,
Okay,
yeah,
but
there is.
there's traces of there might be something
Yeah.
else. Okay, thank you.
I was just wondering if you had like, for the residual plots we're showing, you have one of the, in the column is the beam correction one. You don't have that residual plot, do you?
No, I haven't tested that with, after I matched the pipeline.
Oh,
It's
okay.
on my list.
Okay,
We actually want to switch off the beam correction and see what happens.
right.
Yeah, definitely. The beam correction has been questioned a couple of times. We definitely will switch it off and see what happens. Yeah. So, yeah, so moving on to the other experiment that I work on, OVRO-LWA. It stands for the Owens Valley Radio Observatory, Long Wavelength Array. Not too far from LA, so I've been there like 4 or 5 times, even though I've been involved with that project just for a year. So it consists of about 352 cross dipole antennas, dual polarized antennas, fully cross correlated, and the frequency range we are aiming for is about 12 to 85 megahertz. I like to put this plot up because it actually also targets dark ages and cosmic dawn. Of course, at low frequencies, ionosphere will start being a problem, but it's interesting. We're trying to probe that low. It's currently in stage 3. I'll tell you what the different stages are. And this is our extensive team. So the more the antennas I guess you need more members in your team. It's a much bigger team than edges. Anyway, so some nice photos from the field. And okay, so stage 1 was operation between 2013 to 2014. We had about 251 antennas and only 5 outreachers. This was the single snapshot image from them. If I show you the current stage 3, this looks very okay. And then we moved on to stage 2. It was between 2015 to 2020. You can already see the image quality is improved because we've added about 32 outtriggers at this point. Our longest baseline is about 1.5 kilometers. We are currently in stage 3, and it's an NSF funded project. And you can see now we have grown. The number of outtriggers, total number of antennas have become 352, and we're about an order of magnitude of 80 outtriggers. And the complete other important thing is the analog chain in the back end has been completely revamped, and that is definitely helping. And right now we have the science commission phase. Some beautiful data is coming out of it. So this is very fresh out of the press, literally. It's from Greg Halden. I did make a similar plot, but I couldn't get the scale as similar to his. It didn't look as pretty as his. So this is what we call the high band data. So start from 40 megahertz. And this is just 10-second snapshot. These 2 plots are about 10 minutes of data. A lot of interesting things to come. With this, just with the upgrade, we are ready. I think, in my opinion, we are ready to do 21 centimeter cosmology. To give you, I'll tell you why I'm saying that. So here, what I'm showing you are all possible upper limits that have come out from different interferometers doing 21 centimeter cosmology. So this is your power spectra versus redshift or frequency. So cosmic dawn is this side, lower frequency. Now the bright red star there is the upper limit that came from OVRO-LWA in the stage 2 data, where we had only 30 outtriggers and not as sensitive, and a backend was not revamped yet. There was a lot of crosstalk in our analog receiver chain. And it was quite competitive already. So I'm just excited, just with like the new data, I think OVRO-LWA is designed to be a great cosmic dawn instrument. Also, for comparison, Hera is a 21 centimeter cosmology instrument, but it has been designed for EOR band, much higher frequency. Then as an afterthought, people are using it for a lower band, but OVRO has been designed to be optimized between that 15 to 80 megahertz. So it's an interferometer for the first time dedicated for cosmic dawn band. And they designed the analog chain to minimize crosstalk to the level that's good for cosmic dawn. So with that, this is the pipeline we are looking at. The people working on this are Ruby Byrne, the Caltech, ASU, Danny Jacobs, Judd Bowman, Matt Kolopanis, and me right now working on this. The overall view is that we have an RFI flagging, and we have a dedicated expert, if I may, Greg Helper, who joined us from LOFAR, testing out different RFI schemes that we know for interferometers and seeing which is best for cosmic dawn. And then we have the calibration pipeline, where we will create model visibilities using a sky model beam, which is where I come into play. I'm working with the beam extensively. And then we will use the calibration scheme that Ruby Byrne has developed. And then finally, for the imaging pipeline, we might use the FHT module for folks who know, that was developed by folks at University of Washington. And the other important thing I must mention, the sky model that we're using is the M-mode analysis that was developed by Michael Eastwood and now being taken over by Sander Hall and improved with the new data set. Okay, so why do we care? I want to just talk about the beam, which is what I focus on. Why do we care about the beam? If you think it's too long to go over this, I have my own problem. No. Please don't do that. Please don't mess up my answers. But the idea is, again, like I said, when your signal comes through the beam, it gets, so any foreground will have certain spectral structure. But when it gets convolved with the beam, it has additional spectral structure. So there are two ways of doing this. You either subtract it out, but then if you don't know your beam model well, your residuals will leave higher frequency components that will leak into the frequency modes of your cosmological interest. Or even if you try to suppress it, like use a wedge mode, wedge analysis for folks, so we try to just say any slow varying component, we will not access that area for cosmology analysis. But when you convolve your beam with the foregrounds, that wedge increases and your window of observation reduces. So it's very important to know your beams. So the first thing I did was, the way I'm trying to do this beam analysis right now is simulations. We have spoken about doing some measurements, but you can ask me later on, that's a little complicated to do, but there's some ideas. So for now, we're going to rely on simulation. So what I do is I take the actual dimensions of the antenna over the ground plane, put it over actual soil properties, use an electromagnetic solver like FICO. And it's very important to note that what I'm doing here is you have to have an electromagnetic solver that will model your ground as infinite. There are folks who have done this beam modeling with different solvers that have finite soil and a boundary condition. That artificial boundary condition creates ripples, which give me additional chromaticity on the beam that's not true to the beam. So it's very important in folks thinking about ground plane effects. So I use that. So now the idea is, it's just modeling. There are a few steps that I go over this. So I have one antenna model, and you get a beam. And then you see how your visibility flows. But the idea is we will add more antennas because it's an array. When the antennas talk to each other, there's mutual coupling that will change the beam. I'll show you some plots. You add more antennas, again see the visibility, see if that captures what the data see. And if that's not the case, we'll add even more antennas. And you keep doing that till your beam converges and you see there's no more changes of effects of adding antennas. Okay, so this is the pipeline I have for the beam analysis. So the first step is to take the antenna array location and one antenna model in FICO. And this first step, I am, for folks, if you're doing antenna modeling, I have a little script that now automates this. You just have to give FICO your antenna position and one antenna model, and it'll automatically generate the array for you however large you want. And once you have the beams, I just literally take out the beam models and I do some analysis. We do a delay spectra analysis. We see how it changes. From there, we go into something called the PyUV sim and PyUV data. We take the beam, we convolve a sky model, get model visibilities, then take the delay spectra of the model visibilities to see what your beam has done to the sky. So this is what I've done for initial simulation. This is all the antennas in the core of LWA, which is about 288. But I have just simulated this central, what I thought was close enough cluster in FICO. And this is what the plots look like. So what I'm showing you here are plots at one frequency, but a 2D spatial map, and it's the difference plots. Now, each of these are the antenna beam in the array or in the cluster, difference from an isolated. So if this particular antenna, you kept it isolated with nothing else close to it, you'll have one beam. I'm subtracting that from in the cluster. And you can see the variations about plus or minus, it's about 6%, and it's considerable. And this is just a tiny core inside. And the next thing that I look at is for cosmic dawn, it's nice to do a delay spectra. Take along frequency, take a Fourier transform, because you want to see if all your power of your antenna is like at low modes and is it clean on higher modes where you can do a detection. So if you look at just one of these plots, the black curve is an isolated antenna. And you can see at about 100 nanoseconds, the power is suppressed to the level you want, let's say 10 power minus 4. The rest of the antennas are the antennas modeled in the cluster. So they're talking to each other. Now their mutual coupling has increased the power at higher modes, making your 10 power minus 4 reaching at about 200%. So this is what I'm talking about. It is important because you're reducing your windows of observation. The next thing, that was just like taking the beam directly. So now what I'm doing is I'm using the beam and convolving it with a sky model, and then taking the delay spectra. Now this looks even more drastic. So this black one is the beam isolated. The orange, green, and blue are different baselines of visibilities using their mutual coupled beams. And you can see they do have increased by at least 2 orders of magnitude. This is worrisome. And if you don't model this, this could like really hamper our detection. So that's what I had in terms of OVRO-LWA. So OVRO-LWA, we have the science commission in place, the pipeline is in place. In terms of beam, I have a pipeline as to how we will model it. That might be fine, but what am I going to do with it next? I might model it and I might be like, this is an issue. The idea is I want to use my mutually coupled beams in the calibration. So we calibrate it against the right visibility. But how do I give my calibration code 352 beams? It will be computationally challenging. So what I'm thinking of now is I model, let's say 6 antennas, and I will see if I can have an analytical equation connecting the free space beam with a mutually coupled beam. Can I have a primary beam and what called as differential beam that will capture where you are in the antenna? So that's what I'm looking at. If I have a minute, I know it was mentioned that you'll also talk about VDI efforts here, and there is all of this research is close to my heart, but there's an initiative that I started a couple of years ago. I am where I am today with all my mentors, and also after breaking a couple of biases and stereotypes in my family. I'm probably the first one to leave the country, and also like the first one to get anything more than a bachelor's. So, but I don't want to stop. I don't want it to stop there. So my friend and I, my friends at Amazon right now, we have started an initiative called Letters for Our Girls, where we highlight South Asian women from all walks of life, and basically to serve as a source of inspiration and to show young girls back in India that there's more to life than your parents expecting you to get married. I'm not kidding. So we have an Instagram page and a LinkedIn page, because you know now kids are on social media. And what do we bring to the team? Like I said, just highlight and appreciate accomplishments of different South Asian women. Show them that role models are not far from home. It's right us, right here. Breaking stereotypes. And without going overboard, I think for me the main part is I think inspiration is supreme. And your life doesn't have to be like the person you're inspired by, but just the inspiration makes you want to do more. And what we have planned next is it'll be like a connect letter pen pal situations. We want to connect every woman we were featured on our page to girls and women back in India for them to imagine a life that their family might say no to. Yeah. And I will give it up with a picture of my daughter.
Well, I have a couple of questions, but I'll only do two. So, um, three is it. So first I was wondering, what you're thinking of would be the analytical equation for this differential beam. Is it describing it topologically or just spectrally or?
That's a good question. Spectrally is what, no, actually, no, I stand corrected. It has to capture both.
Yeah,
I'm thinking like, it has to capture it varying in theta and phi simply because it has to get the 3 dB varying frequency. So it has to be both spectral and the 3 dB variation. Yeah.
okay.
Do I have an idea of what it is? Yeah.
Yeah. No, I've been thinking about that a lot too, because we were trying to also analytically model them, but, and my other question is there any thought about like trying to use the OVRO-LWA antennas separately, all in like global signal
Oh,
mode?
yes. We have lots for that. So that is something I am looking at. First thing I did was just look at the chromaticity of these beams. It's horrible.
Great.
So we have to think of something has to be modified. Either the ground plane has to be made large, or it's okay, use the receiver electronics, just modify the antenna. Let's just use a different antenna. I think it might be easier. So we are definitely actively thinking about it. It's not just for the global 2050 signal. The cosmic ray detection team also wants an absolute flux measurement. So this will be useful for them too. So we're thinking of it, yeah. No, sorry.
Okay, I was like, I just want to make sure, since I already also asked a question. So it seems like you're doing mostly like coding work, but then you also get to travel out to the site. So I guess I was just wondering if you could talk a little more about like doing hands-on stuff and analytical stuff and like what your job entails,
Yeah,
I guess.
okay. Yeah, that's a good point. Okay. With edges, I didn't get to go to field, even though for almost 2 years of my PhD, I was just modeling the antenna, and it was so annoying just looking at pictures. And then there was one point where like Judd, who's the PI of edges, he was like, "Oh, we modified the capacitance. So the dipoles are like this, and above that there's another capacitance plate. So the memo has some height. The pictures show me something." And then he's like, "Oh, I'm sorry, we forgot to record this, but then now the height is something else." And that changed the S1 dramatically. And I'm like, I think it's time I go to site. But no, that didn't happen. Somebody else went to site and they gave me the measurements. But okay. So ASU, it was not much on site, but at OVRO-LWA, it has been a really nice experience going to site. Simply because, so a couple of things. I did an S11 measurement of the antenna because, okay, so I didn't mention this. So we do a lot of simulations of the beam. How will you trust it? I was expecting one of you to be like, how do I trust this thing? The only one thing you can measure, you can't actually measure the beam, even though there are efforts for that, we can talk about it. One other straight measurement you can get from the antenna is the reflection coefficient. There are two things you get from the antenna. Either the beam, measure every point of the beam, or get its reflection coefficient. So I went on site, made one of those measurements, checked my model was giving me that. If it didn't, I would plug in my measurement into my simulation software and leave a few parameters I think I could have got wrong, and then it's optimized by my beam model. Yeah, you know, so that is like a feedback. So I trust my beam simulation to some extent now. Yeah. But I enjoy field work. I do. I just need more opportunities or excuses.
Yeah.
So, yeah.
I was wondering, you said that it would be computationally expensive to actually see the combined effect of all 52 antennas. So you are basically creating an analytical model to predict, right?
Yeah.
But even if you made the analytical model, how would you reconcile it without actually, seeing the true effect from the all 52 antennas?
Okay, so there are two things. The computational expensive could be me modeling all the 352 antennas, which I'm not too worried. It could take a couple of days. What I'm worried about is once I model them, I have 352 beams. Putting that into my simulation where it's like now 352 squared baselines, that is where it could get computationally expensive. But your point of like, at some point, maybe I will simulate all 352, But that also I'm going in clusters, like I said. Now I'm simulated 6, I will simulate 10, I'll simulate another 20 maybe, and see if the central most antenna is changing in beam. After a point, if the difference is not much, and that's But it may, if it requires, if I see the distance, the difference matters, then I will keep at it. Yeah. Yes.
So you showed that with the updated APS-3 and possibly once you do the new pipeline apply, that the initial 2018 result seems to be persistent. I think are you increasingly confident that's real? And if it is, what are your hunches on what it actually means for the cosmic dot?
Right. So I think it's real. Alan has never been wrong. Oh no, but it would be interesting. I'm not going to just obviously say that without running through my pipeline. But if the new pipeline also shows that, there are a lot of theories. How do we confirm the theories? I don't know much details about it. If anybody else knows, feel free to chime in. One of the interesting things would be to get a confirmation from 21 centimeter the interferometer result. So different models that theorists have predicted because of the edges signal show slightly different features in our power spectrum detection. So OVRO-LWA, low fast detection, if they all can probe to the sensitivity we need in that 78 megahertz band, could sort of narrow down a couple of models, theory models. The other useful thing would be to probe dark ages. Because again, some of those cosmology models invokes really crazy non-standard cosmology physics. And the easiest playground to test that is dark ages, where no other sources have turned on yet. So you can really test the lambda signal model. And so that would be useful. That's where, again, we really need lunar observation. Right.